أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم.
In this session, we are going to talk about evaluating structural model predictive power, that is step 4 of our structural model assessment. Now, many researchers interpret the R-square statistic as a measure of their model's predictive power. This interpretation is not entirely correct. However, since R-square only indicates the model's in-sample explanatory power, in-sample here refers to the data that you have, and out-of-sample to the data that you do not have but want to forecast or estimate. So R-square has got the capability to explain or provide explanatory power with respect to the sample that you have. However, you cannot estimate the sample that you do not have, that is out-of-sample prediction is not possible. It also says nothing about model predictive power, that is referred to as out-of-sample predictive power, which indicates a model's ability to predict new or future observations. So you cannot predict new and future observations based on R-square. Now the question remains, does the model has good predictive quality? Because at the end of the day, we are using these techniques for prediction. Addressing this concern, Shumeli and others in 2016 introduced PLS Predict, that is a procedure for out-of-sample prediction. Now, execution of PLS Predict involves estimating the models on training and evaluating its predictive performance on the holdout sample. Execution of PLS Predict involves estimating the model on a training sample and evaluating its predictive performance on a holdout sample. Now your whole data set is actually divided into two subsamples. One is your training sample, you can call it sample 1, and the other one is your holdout sample, that is your held out sample, that is called sample 2. Note that the holdout sample is actually separated from the total sample before execution of initial analysis on the training sample. So it includes data that were not used in the model estimation. So initially the estimation is based on training sample. Now researchers need to make sure that the training sample for each fold meets the minimum sample size guidelines. So although you are dividing your sample into training and holdout sample, your estimation, in order to be correct, the training sample has to have met the minimum sample size guidelines. And for that you can see the following inverse square root method, and that link will be shared in the description. Now execution of PLS Predict involves estimating the model on training sample. So your estimation is done on training sample and evaluating its predictive performance on the holdout sample. So your estimation done on training sample is then used to predict your holdout sample. Note that the holdout sample is actually separated from the total sample before executing the initial analysis on the training sample. So your training sample is removed from your holdout sample. Now there are 5 folds here. PLS Predict executes k-fold cross-validation. A fold is a subgroup of the total sample. So here is fold 1, fold 2, fold 3, fold 4, fold 5. That is, the total dataset is randomly split into k equally sized subsets of data. So your sample is divided into subsets of data. Now for example, let's say we've got 5 folds here. K is equal to 5. Normally 10 is recommended. Now in this case, each fold is divided into holdout and training sample. So if you've got a data, let's say 100 is your sample size. Let's say we've got a sample size of 100. Now if that is divided into 1, 2, 3, 4 training and 1 holdout sample, so there'll be 20 here, 20 here, 20 here, 20 here, and 20 here. Now this here is your holdout sample and this here is your training sample. So your estimation is done on training sample, and based on that estimation, your holdout sample is predicted. Now, this is for fold 1. Now, in fold 2, what happens is, in fold 1, let's say this was your holdout sample. In fold 2, this will become your holdout sample, and the same estimation will be run again. In fold 3, this will be your holdout sample, and the estimation will be done again. And similarly for the next 2 subsamples. Now, moving on. PLS Predict then combines K-1 subsets, that is 4 groups of data here, training, these 4 groups combined into a single training sample that is used to predict this particular 5th holdout sample, as we described just earlier. Holdout sample is predicted based on the training sample. Each case in every holdout sample has a predicted value estimated with the respective training sample. So your holdout sample predicted based on training sample, your holdout sample predicted based on the rest of the sample. Again, your holdout sample keeps changing unless or until you do for all the folds. Now, a training sample is a portion of the overall dataset used to estimate the model parameters, that is the path coefficient, indicator weights, and loadings. The remaining part of the dataset that is not used for model estimation is your holdout sample. And the training dataset is used to estimate, that is, train the weights and paths of our model, and then we use these estimated weights to predict the outcomes in your holdout sample. So in short, your training sample here predicts your holdout sample for each of the folds. And then we evaluate our prediction matrices based on whatever analysis has been done. And there are multiple ways to do this prediction. We do not compare predictions of training and holdout samples. And finally, the K10 is recommended. Now we are going to look into this. This is by default 10 in SmartPLS. Now, the generation of K subsets of the data is a random process and can therefore result in extreme partitions that potentially lead to abnormal solution. Now, to avoid such abnormal solution, researchers should run PLS Predict multiple times. Now, to assess a model's predictive power, researchers can draw on several prediction statistics that quantify the amount of prediction error in the indicators of a particular endogenous construct. So, you look into the error or prediction error of the endogenous construct. Error in here is not an error as in mistake. It is a residual. The lower it is, the better. This is the difference between your actual values and the predicted values. And you want your error to be minimized. You want your values, that is your actual values, closer to the predicted values. And if that's the case, you have high predictive power. Now, the most popular metric to quantify the degree of prediction error, how do you assess the degree of prediction error? You use this particular metric, root mean square error. We have used this in AMOS as well, and in SmartPLS now we are going to use it. Now, another one is MAE, mean absolute error. Now, which one to use? In most instances, a researcher should use RMSE. However, but if your prediction error distribution is highly non-symmetric, that is, there is a long left or right tail in the distribution of prediction error for the endogenous variables, then you are going to use MAE. SmartPLS will provide you the graphs for it. Now, to assess the degree of prediction error, use the RMSE unless the prediction error distribution is highly non-symmetric. In this case, the MAE is more appropriate prediction statistic. Now, to interpret these matrices, researchers need to compare indicators RMSE or MAE based on the prediction error with the naive linear regression model. Now, what you do is you compare these values here with your linear regression results. So what if you used this model and tested it based on linear regression and then you tested it based on PLS? Is there any difference? Now, your prediction error should be minimum when you are using PLS instead of using linear regression model. So a higher error in linear regression model and lower error in RMSE would mean that you've got high predictive power. Now the linear model, that is linear regression model, benchmark values are obtained by running a linear regression of each dependent construct indicators on the indicators of the exogenous construct in the PLS path model. So what happens is you are simply running linear regression model whereby you are assessing the impact of the exogenous constructs in the PLS path model, that is the indicators of the exogenous constructs on the dependent constructs indicators. And then you compare the RMSE values with the LM values. And these are the guidelines that we are going to use. Now, when all the indicators in the PLS SCM analysis have low RMSE or MAE value compared to the naive LM benchmark, the model has high predictive power. Now, if the majority or the same number of indicators in PLS SCM analysis yields smaller prediction errors, not all but majority, then you've got medium predictive power. Now, if minority of the constructs indicators produce lower SCM errors compared to the naive LM benchmark, this indicates low predictive power. But when you've got PLS SCM analysis yields low prediction power, that is RMSE, for none of the indicators, that is the prediction error is higher in RMSE or MAE in comparison to the linear model, then you've got no predictive power. So if your RMSE values are lower in comparison to your naive LM benchmark, then you've got model's predictive power. But then if all, majority, minority or none, you have to compare based on these guidelines. Now these are the guidelines for using PLS Predict. If your Q-square predict is greater than 0 and you check for prediction errors, if they are symmetrically distributed and they are not too extreme, use RMSE and check if PLS SCM has lower prediction errors in comparison to naive linear model. For none of the indicators, then you've got serious issues. For minority of the indicators, then low predictive power. Now, most of the RMSE values for PLS SCM are higher in comparison to the LM benchmark, then you've got low predictive power. Medium for majority of indicators, and if all of the indicators in PLS SCM have RMSE value less than the naive LM benchmark, then you've got high predictive power. Now, how do we do this in SmartPLS? Now, how do we use PLS Predict in SmartPLS? So I'm going to use PLS Predict to check the predictive power of this model. Let's go to Calculate, PLS Predict. Number of folds 10, number of repetitions 10. We have already looked into it. Partial least squares, path, and start. Now here are our results. PLS, LM. So we've got the prediction summary for our manifest variables, and this is what I'm interested in now. We can have latent variable as well, the RMSE, the MAE, Q-square predict. This is good for latent variables. But we are not interested in assessing this for now. We are interested in assessing these values here. So the first step is we go to PLS manifest variables, MV manifest variables, histogram. And we are going to assess if we've got highly skewed distribution of the residual errors. Now look at this. Well, it looks symmetric to a certain extent. Look at this. Well, long tail, not that long, but long. Again, you have to do it for all of them. Most of it is in the middle here for most of them. You cannot say it's highly asymmetric. This is fine. This is left-tailed, 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 but so overall it's not highly asymmetric. The tails are not that long. So it is not too long left or right tailed. So yes, we can go for RMSE. If you think that the tails are too long, you can use MAE. The option is there to be used. So for now, we are going to stick to RMSE, that is mostly utilized. So how are we going to do it? Let's go back to our output. Once you have seen the histograms here, PLS MV error histogram, now come to MV manifest variables prediction summary. Here it is. So I'm going to compare here these RMSE values here, the PLS, with the linear model. So if this model would have been assessed based on linear regression, simple linear regression, these would have been the RMSE values. With the PLS model, the proper measurement and structural model, these are the RMSE values. The discrepancy between the actual and predicted values. And this is the discrepancy between actual and predicted values when a linear model is utilized to predict the outcomes. Now we have to compare the PLS RMSE with linear model RMSE. Now the Q-square is all good. So let's compare these two. So what I'm going to do is, first I'm going to copy the PLS one, Excel format, and let's go to Excel, open, paste, and this is for, let's say, I'm going to use, let's delete these two, and this is PLS. Now let's go on with LM, linear model, Excel format, and paste it here. Let's delete this. For now, let's delete the Q-square as well. This is, if you see here, the Q-square is good enough for your PLS model. You can say it's moderate to substantial. So you do not need these two columns. So those two columns have been removed. Now we've got PLS. This is PLS and this is LM. Now what you can simply do is add a formula. Press is equal to PLS minus LM. So if there is a negative sign, this means LM has got a higher value. Look at this. LM has got a higher value, and similarly you can do it for all of them. Now look at this. Higher, 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 higher. So in most cases, except for one here, where this one is higher, in most cases the value for linear model is higher in comparison to the PLS model. So when your values are higher for your linear model in comparison to the PLS model, and in this case the most of the values are higher, the error is lower in PLS model. If the error is lower, the prediction error is lower, this means your model has got high predictive power. Hence, we can conclude that the model has got high predictive power. Let's go back to a few slides here. Now if you look here for the assessment, the LM benchmark values are obtained by running linear regression, which we have already done. And let's see if all the indicators in PLS SCM analysis have lower RMSE. Not all of them have got it. So you cannot say your model has got very high predictive power, but it is high. If majority or the same number of indicators in PLS SCM analysis yields a smaller prediction error, and yes, in this case, the PLS SCM has got smaller prediction error in comparison to the linear model, this indicates a medium predictive power. But in this case, it's not the equal number. Majority, even like let's say 95 or 96% of the indicators have got low prediction errors. So we can say our model has got high prediction power. And this is how you can use PLS Predict in SmartPLS to assess the predictive power of your model. A quick recap. So the first step here, PLS MV error histogram. And what you do is you look into the prediction error distribution is highly non-symmetric. Well, this is not highly non-symmetric. There is not too much of a long left or right tail. So yes, we can go for RMSE. Now we are going to use RMSE, and then we come to manifest variables. Here, compare this RMSE for PLS with RMSE of linear model. Which one is lower? In this case, I want my PLS model RMSE to have lower values. Now to do so, the easier way is copy them in Excel. I've done that. And then comparison. This is high, high, high. All of them are higher here. except for this one. So out of 13, there are 12 errors that are higher in linear model. So this means that our PLS SCM has got lower prediction error. So this means that your model here has got high predictive power. I hope this session would have helped you understand how to use SmartPLS to assess the predictive power using PLS Predict. Thank you very much.